Hello everyone, this is Shruti. I am going to be presenting our paper, InBiaseD, Inductive Bias Distillation to Improve Generalization and Robustness through Shape Awareness. This is a joint work with Bahram Zunus and Elahe. Deep neural networks are achieving superior performance in a multitude of perception tasks, but there still exist some fundamental shortcomings. Networks tend to focus more on the trivial local cues, thus taking a shortcut. Shortcuts are defined as decision rules that perform well on the current data but that do not transfer to the data from a different distribution. Studies have also shown that networks rely heavily on textures. These behaviors leads to lower generalization performance. Humans, on the other hand, are less vulnerable to shortcut learning and can identify objects irrespective of textural perturbations. This can be attributed to the high-level cognitive inductive bias in the brain. Our goal is to bridge this gap and introduce inductive bias into the networks. We want to introduce meaningful biases that will enable the network to learn high-level and meaningful representations. Hence, we propose InBiaseD. InBiaseD distills prior knowledge from an implicit information already existing in the data. We focus on shape as one of the meaningful inductive biases, as it is also observed that humans focus more on the global shape semantics to make decisions. Our method does not need any additional requirements in terms of data or meta-information. Through extensive analysis, we show that InBiaseD reduces shortcut learning and texture bias. Further, it also helps in improving generalization performance and robustness. Our method involves two networks. One receives the original RGB data and the other receives the corresponding shape information respectively. We train the two networks in synchrony and introduce a bias alignment objective to align the two networks. The bias alignment objective provides the flexibility to the network to learn on its own input but also align with its peer network. This happens in two spaces, the feature space and the prediction space. Hence, InBiaseD learns both the original and the shape data, which helps in exploring more generic representations and reducing overfitting to trivial solutions. The shaped images are extracted by using Sobel algorithm on the original RGB images. The decision alignment between the networks is performed in the prediction space to align the network's probability distributions. So the decision boundary alignment is now incentivized by the supervision from shape data and hence allows the networks to make decisions that are less susceptible to shortcuts. To ensure the shape supervision even at earlier stages, we use the feature alignment to maintain consistency between the features of the two networks in the latent space. The overall loss function is the sum of the classification loss and the two alignment losses. To measure the vulnerability of the models to shortcut learning, we perform spurious correlation analysis. Spurious correlations are the unintended associations present only in the training data and might not translate to test settings. For example, as the first dataset, tinted STL10 is created by adding a class-specific tint to the original STL10 data. The training data has this spurious correlation, which is the class to the background tint, while the test data does not. The performance graph shows that InBiaseD is less vulnerable to these induced correlations. We also investigate this effect on two other different datasets. We inject similar spurious colors into the MNIST dataset to create three versions of colored MNIST dataset. InBiaseD gains a significant improvement on all the versions. For the third dataset, we consider celeb A and create a skewed celeb A dataset which consists of only blonde females and non-blonde male samples during training. The test set contains all the four possible combinations of hair color and gender. As seen, we observe better generalization to the blonde male and non-blonde female categories, which was not present in the training distribution. To precisely view what attributes the model is relying on to make the decisions, we use GradCam to visualize the attended image regions. As seen in the figure, for tinted STL10 dataset, InBiaseD focuses on the object-relevant features, such as aircraft wings or the beaks of the bird, while the standard network focuses more on the task-irrelevant background information. On the skewed CoLLA dataset, the baseline model relies more on the unintended cue, which was the hair color, while our method relies more on the salient facial features of the face to make the classification. Another test to show if models are indeed learning high-level abstractions is to apply a transform that changes the statistics of the data without altering its high-level semantic details. Fourier Filter is one such transform that changes the statistics of the images while still preserving the recognizability of the objects from a human perspective. The Fourier filtered samples at varying radius trends are depicted in the right-hand side of the figure. As shown from the graph, InBiaseD performs better and is hence less prone to learning these superficial attributes in the data compared to the baseline. Overall, from these two analyses, distilling inductive bias shows promising results in the direction of tackling the challenges of shortcut learning. To test if our method has reduced the model's bias towards texture, we perform a texture bias analysis. We apply style transfer of varying strengths on the tiny ImageNet dataset, and these are evaluated using a model trained on the original tiny ImageNet dataset. Some samples are shown on the right. InBiaseD generalizes better on the stylized images compared to the baseline. As these stylized images have different textures, the model needs to have learned more than just local texture information to infer well and classify them correctly. Thus, InBiaseD proves a successful step towards making networks more shape-aware and overcome the challenges of texture bias. DNNs are shown to be extremely sensitive to the adversarial perturbations. To analyze the adversarial robustness of the models, we perform a projected gradient descent or PGD attack of varying strengths. As shown in the graph, InBiaseD shows more resistance to the attacks and has higher robustness across all the attack strengths. These encouraging results prompted us to further explore the effect of adding our method to standard adversarial training schemes. We employed two existing adversarial training schemes, Madri and TRIPS. We then plug in InBiaseD into these frameworks seamlessly to perform adversarial training. Out of the two networks, the first network sees the adversarial images while the second has access to the natural images. Adding InBiaseD as a plugin, as shown in the numbers, shows a gain in both the natural and adversarial accuracy. Thus, distilling shape awareness shows promising results in achieving better trade-off between generalization and robustness of the models and opens up new avenues for exploration. Models must not only be accurate, but should also indicate when they are likely to be incorrect. In safety-critical applications, models need to be highly accurate while also being reliable. So hence we perform a calibration analysis. The calibration error scores and reliability diagrams for 4 datasets are shown in the graph. The baseline predictions are overconfident for all the datasets. InBiaseD shows significantly lower error and hence is better calibrated. For example, in the challenging OOD dataset ImageNet R, or it consistently generates more prudent predictions and hence is more suitable for safety critical applications. Finally, we tabulate the generalization performances on multiple datasets belonging to IID or the independent distributed or OOD, which is the out of distribution, and shortcut learning distributions. We also compare against other techniques used in literature to improve generalization, such as self-distillation and deep ensemble. InBiaseD performs comparable or higher in all the datasets, while on shortcut learning, the improvements are more significant and prominent. Thus, to conclude, InBiaseD was proposed to tackle shortcut learning and texture bias present in deep neural networks. InBiaseD distills inductive bias knowledge into the neural networks in terms of an improved shape awareness. As seen from the multiple analysis and results, InBiaseD is less susceptible to shortcut learning and texture bias behaviors. Further, InBiaseD also shows improvement in robustness to adversarial perturbations. Moreover, InBiaseD also results in a better trade-off in generalization and robustness when it is plugged into the standard adversarial training schemes. Lastly, it also achieves improved generalization to both IID and OOD data distributions. Thank you.